there are two kinds of inductance. One is mutual, and the other one is self-inductance, right? So let's say if we have an inductor, right? If we have an inductor and right, and let's some I current is flowing through it, right? So then there would be some another EMF that would be induced due to this current I, right? And the flux generated into this coil that would be directly proportional to, right? This is uh, this is self inductance. So how much is this self inductance? So we know that the flux, let's say in this part, let's say we only talk about this part. So this 5 prime would be proportional to this current which is flowing, and that would be equal to that 5 prime would be equal to Li, right? And this is called the self inductance. And we know that the total inductance would be how much? Total inductance, because there are n turns, right? There are n turns, so total inductance would be how much? That would be n 5 prime. And that would be how much? So total flux would be n and Li. So this is the thing, right? And we also know that let's say let's say how much is this from Faraday's law? What do we know? Right. So let's say this is phi, right, and this is equal to n L I. And from Faraday's law, we also know that EMF that would be equal to how much? That would be equal to d phi by dt, right? And this would be equal to how much? That would be NL and di by dt, right? Or if we calculate, if we calculate the flux from the general definition. So what is the definition of the magnetic flux? What is magnetic flux?
d5 by dt.
No, no, no. So magnetic flux, not the EMF. EMF is d phi by dt. I'm asking about what is the magnetic flux. What is flux?
So ba cos theta.
Pa cos theta, right? So Pa cos theta and theta is 0 degree in this case. So we'll only write Pa, right? And this is equal to NLI. And we know that how much is the magnetic field inside this thing. So how much is that? How much is the magnetic field inside a solenoid? How much is that? Yeah. So the magnetic field inside the solenoid is mu naught n I, right? Is it clear?
Yes, sir.
This is mu naught n I and A, and that is equal to n L I, right? So then if we calculate or if we compare this thing, right? If we compare this thing, so that would be how much? Oh, so we should calculate first, right? We should write, yeah, right? So this phi is only L I, right? So this n phi prime, that is L I, And we know that this 5 prime is how much? So that is BA, right? And this is equal to Li. So we write this B, so that would be how much? This would be mu naught N I A, and this is Li. So if we write this number density, right? So that would be how much? That would be how much? Or if we write this N, so that would be how much? This is N, and let's take this length to be L. So from here to here, we are taking this length to be L. This is NL. This is mu naught. This is NIA, and this is LI. So this I will cancel, and we will get the self-inductance as mu naught N square and L and A. So that is the self-inductance, right? Is it clear? So this is how we calculate the self-inductance. So this you have already done in the CBSE portion, right? Do you remember this, Tariq? Yes, do you remember it?
Yes, sir.
Yeah, so do you remember this result?
Yes.
Yeah, and similarly, the mutual inductance is what? So let's say if you have these two.
So in the self-inductance would be just nu, right? Nu L square nu N square LA.
Yeah,
In the
yeah.
school we
So
learned it like that.
yeah,
Not nu
yeah,
not.
yeah. So you remember new.
Yes, we did it as a nu not nu. We took it as like that.
Oh, so you remember like mu n square LA. You remember
Yes.
like so this mu would be there if this inductor is in some medium, right? If it is some in
Okay.
medium, then
So
this
in
would
school
be,
they didn't talk about, yeah, we just did it. They didn't say about the
yeah,
medium if it was to be.
yeah, yeah. So if it is in the air, right? Generally, this inductor is in the air, right? Then this would be the mode of the right. So this will convert into mu in the medium. Right. Yeah. So I derived this thing, but yeah, this derivation was not important. So similarly, I will not write the derivation for this. Right. I will not write, and I will only directly write the mutual inductance. So mutual inductance is how much? Mutual inductance is mu naught N1, N2, L square, and E. Right. So this is the mutual inductance. We get L square. Do I need to derive this thing? Do I need to? What is that? What is the mutual inductance? Like, because I don't want to derive, I will directly write, and you just because if we derive this thing, so that will take a lot of time. So how much is mutual inductance? So this is simply, yeah, self-inductance is mu naught n square EL, and mutual inductance is mu naught N1, N1 and N2, and EL. So that is also the same, right? But only thing which is different is that you have different right mediums. You have different mediums. This is also right. So this depends, right? This area depends, and this is again these two things that we have to remember. And then the energy of this inductor, right? So EMF is how much? EMF of this inductor, we know that EMF is minus d phi by dt, and we know that phi is Li, right? So EMF is simply minus L di by d. And if we write only the positive part, so that is simply L di by d. Right? This is the EMF generated in an inductive circuit. And again, we also calculate the energy. So how much is the energy of the inductor? So we know that if we write the work done or power, if we write right, if we write power, so that is how much? How much would be the power? Power in terms of voltage and current. How much would be the power? Yes. How much is the power?
Power. mm,
Power is voltage
Yes,
into
P.
current.
P.
Yeah,
It can
right.
be also I square RT, right? Some formula system.
Okay, no, no. That would be I square R only, right?
I square.
So we don't have, let's say, we don't have resistance, and yeah, we don't know about resistance. We only have this voltage and current, right? So power would be simply VI, right? So I can write this as EI, and that would be small rate of doing what? Is that clear?
Yes, sir. Clear.
So I can write this dW by dt as E value I can write, so that is di by dt, and then I. So I can cancel this thing. So dW would be Li di. And if I want to calculate the energy, right, so that would be W, which is delta U. So that would be, I will get half Li square. So I will write it directly, right? So this is the energy of the inductor that you get. Clear? Yeah, is it clear?
Yes, sir. Clear.
Okay, so quickly, yeah, quickly note these things down, and then we will move on. So then we will do some questions. And then this chapter would be over, and please note. So we only have to remember what is the self-inductance, right? What is the mutual inductance, and what is the energy of the inductor. And on the basis of this thing, there are some questions. Yeah, whenever you want me to scroll down, please. Yeah, whenever you want me to scroll down, please tell me. I have written 5 prime as LI, so this 5 prime should be N 5, right? And yeah, so then I can write this N phi, and then I write, so then I write the value of phi. So phi prime is whole flux, right? And this whole flux is equal to the N into these flux. That is, yeah, whenever you have noted it down, please tell. Then, Tariq, yes,
No, sir, I'm
Tariq,
doing.
yeah, be done because we have to some problems and then we move on.
Can you scroll down?
Yeah.
So is it the same derivation for mutual inductance?
Yeah, is it the same? What?
Is it the same derivation, like similar?
Yeah, same derivation. So only I didn't do the derivation part because you have done it in the CBSE portion, right? So if we do it here, so that will take some time. Derivation is same, right? We have to find out,
Yes.
right?
Yes.
Let's say if you want to find out mutual inductance of one due to two. So then uh, that thing would be, let's say, phi two, right? So let's say you have, let's say this is I1 current, which is flowing, right? So this I1 current will generate the flux in this secondary coil. And that would be how much? That would be I1, right? And then you calculate all this flux in the second coil. So that would be magnetic field in due to this one coil, and then area of the second coil, and all these things you calculate, right? And this would be n, and let's say this would be in n2, right? So n1 and this b1 would be n2, and then you calculate all these things, and then you will get this m12 as yeah. Derivation is not that important, but the idea would be same. Okay. And you have also already done this in your CPSC portions. That is why not. Do you want me to write the derivation?
No, sir, no, sir. I'm just asking.
Yeah, yeah. So only we have to remember that. We have to only remember that if we are taking I1 current, this I1 current will generate the flux in the secondary coil, right? So then the flux would be in phi 2, and that would be proportional to M12 and M21 and then I1, right? That is, yes. If we are generating the flux in secondary coil, so that would be mutual inductance in 2 to 1 I1. This is the only thing that we have to do. Or if we are generating the flux in the first coil, primary coil, so that would be equal to M12 and due to current I2, right? And in final state, we will prove that this M21 equals to M12. So these are the two things that we have to do, right? Yeah, so this is the only thing that we have. And for both the cases, we'll get so quickly note it down, and then we have to do some questions, right?
Can you scroll down?
Yeah, whenever we have completed, please.
Yes, sir. Hmm.
Then, okay, so then we have this question which is related to self and mutual inductance. And if we do this problem, then it's the question is that uh, there are solenoids which are full axial with number with number density number density as n1 and n2, and radiuses. Please join this link. Which link we have to waiting participate. Oh, waiting. So that is okay. These there are two solenoids which are coaxial with the number densities as n1 and n2, and radii r1 and r2 respectively. Right. Find the ratio of mutual and self inductance of the inside coil of radius r, right? So we have what do we have? We have this first solenoid, right? And we have this another solenoid which is inside. So this one has dimension I1 and let's say N2, and this one has let me write it as 1. This one is N1, R1, and I1, and so on, right? And then this one has dimension N2, N2, R2, and so on, right? So then I want to calculate the mutual inductance ratio of, yes, hello, Jabbar. So, yeah, did you get the other link? Because this is the wrong link that you are entering, right? Yeah. So, what do we have? We want to calculate the mutual inductance in this coil, and we want to calculate the self-inductance into this coil, right? So, what would be the mutual inductance in this inside coil? That would be mu naught N1, N2, and area would be how much? Area would be, let's say, pi R2 square, right? And let's say this distance is L. So that would be L, right? This would be the mutual inductance, right, Tariq?
Yes, sir.
This would be the mutual inductance, right, in
Yes,
the
sir.
inside. And now you tell me what would be the self-inductance inside. So this is we are calculating inside. What would be self-inductance inside? How much would be that?
Yes, sir. New naught L square
Yeah, but what
N
would
square LA.
yeah, but what
No, N
yeah,
N
what
square pi R
yeah.
pi R
So
pi R
we
square.
know that, yeah, absolutely, you are going in the right direction. This is mu naught n square AL, right? But
Yeah.
what would be, what n we will choose? We are calculating the self-inductance inside, right?
N2.
This is N2 ohm, so this would be N2. Yes, N2 square and pi R2 square.
L.
Right, is this clear?
Yes, sir.
So then if we calculate the ratio would be how much? M by L, so that is mu naught N1 N2 pi R2 square L divided by mu naught N2 square pi R2 square L. So this mu naught will cancel, L will cancel, R2, R2, all these things cancel, N2 will cancel, and we get N1 by N2, right? So whatever is if this would be this thing, and if N1 is inside, right? Then what would be the ratio? Then ratio would be how much? Then ratio would be N1 by N, N2 by N, right? Yeah, did you understand this part? Did you understand this part? Yes, Tariq, did you understand this part? Hello, Tariq, can you hear me?
Hello, sir. Can you hear me, sir?
Yeah. Now I can.
Yes, sir.
So did you understand this part? So
Yes, sir.
I'm saying that let's say the dimension you have changed. So let's say the upper one, but the outward one is N2 and R2. Inside one is N1 and R1. Then the ratio would be N2 by N. So this is what I'm saying. Is this clear? Is it clear?
Yes, sir, clear.
Yeah. So then please down, please put it down and then other questions. And whenever you have completed that, yeah, whenever you have noted it down, that this study, whenever you have noted it down.
I'm noting it down. Sir, done.
Then, okay, so now let us do a difficult not it is that okay, so a small square loop of side A and one turn is placed inside a larger square loop of side B and one turn. These are coplanar with their centers coinciding. If a current I is passed in the square loop of side B, then which means that it is in the outer side, then coefficient of mutual inductance between the two loops is right. So we have to find out the mutual inductance right? So we have this loop, and we have this loop, right? And we want to calculate, right? So this is the square loop of dimension A, right? And then we have to find out, yeah, this is the square loop of dimension B. And this one is carrying I1, let's say I current. So I current is passing through it. This I current will create in induction effect, right? The flux effect inside this coil. So we have to find out the mutual inductance of this secondary coil, right? So for that, we have to remember that, yeah, we have to remember that flux in this part, that would be how much? Flux in this coil, that would be how much? And there would be how many contributions of flux that we have to also, right? So can you tell me that, yeah, can you tell me that how much would be, okay, so to do this question, we have to first remember that what is the magnetic field, right? This thing we have to remember, let's say, what is the magnetic field of a finite wire, right? Magnetic field of a finite wire at a distance, let's say, A. So do you remember what is the magnetic field? Do you remember what is the magnetic field?
Can you repeat?
What is the magnetic field of a current carrying finite wire at a distance A from it? At this point, you are calculating the magnetic field. So,
Mu not
yeah,
mu not I to
not I, yes,
I. mm,
yeah. What is, okay, so do you remember what is the magnetic field of infinite wire at this point? What is the magnetic field?
mag- Magnetic field of infinite wire.
Yeah, infinite wire at a certain distance. This you remember, right? Don't tell me that you have forgotten this part also.
Yes, sir.
What is the magnetic field?
Sir.
Yes, what is the magnetic field?
Yes, sir. Mu not I to pi.
Yeah, mu naught I by 2 pi a. That is
Pi.
the magnetic field.
Pi.
But this is for infinite wire. So for finite case, if you remember it correctly, that was mu naught I by 4 pi a sine theta 1 plus sine theta 2. Do you remember this?
Yes, sir.
Yeah, so this is for the finite wire, right? And we can get the infinite case. For infinite case, what is this theta 1 and theta 2 for infinite case? What is this theta 1 and theta 2?
The
Yeah,
one will the first angle and the second angle.
yeah. For infinite case, what is this theta 1 and theta 2? Let's say this
It
is infinite. So
is
this is theta,
yeah,
right?
it
And
is
if you increase this thing, so this would increase, right? So then theta 2 is 90 degree, right? Theta 1 is 90 degree for infinite case. Then you will get this thing as sine 90 plus sine 90. So you'll get 2 and 2 will cancel and you will get back this result, right? So that is how you can remember this finite case. Okay, clear? Is it clear? Yes. Is it clear? You joined. Uh, yeah. So hello, Muhammad. Can you hear me? You are here for what class? You are here? Yeah. You have not joined earlier for this class. So, yeah. Did you get the wrong link or yes, Muhammad? Can you hear? Not replying, right? Okay, so we have to find out, right? So this current will generate some flux, right? This current will generate some magnetic field, and we have to calculate the magnetic field at this center, right? So magnetic field lines would be passing. Magnetic field lines would be passing, and the amount of magnetic field at the center that we have to calculate. So similarly, let's say this is a finite wire. So this contribution, right? This wire will give a contribution, and that contribution would be how much? So we know that phi is mi, right? And phi is how much? That is va, and that is mi, right? And we know that this magnetic field will have four contributions. So one would be due to this, let's say, AB length, and then BC length at this point, right? And CD length at this point, and AD length at this point. So all these contribution would be same because this is a square. So this would be, let's say, 4D1 A, and that is M5. And we have to calculate this M. Right? Is it clear to you, Talib? Is it clear?
Yes.
And what would be the area? What is the area of this thing? What is the area? What is the area that in which we are calculating this flux? The flux is generated in this area, right? So that would be A square. Clear? And we have to calculate the magnetic field at the center due to this R, this wire AB. So let us calculate that, right? So let us calculate that, and we already know this result, right? So how much is this distance? The total distance is B, and this is the center. So how much would be this distance? How much would be this distance? Yeah, we are trying to calculate the magnetic field at center, and this total distance is B. From this to this point, the distance is half of B. So that would be B by 2, right? Clear? Is it clear, Tariq? Yes, Tariq, can you hear me?
Yes, sir.
Yeah, so we want to calculate the magnetic field of a finite wire. The distance is B by 2. And the angles are equal, right? Because these arms are equal, so this is equal and this is equal. So this would be 45 degree, this would be 45 degree. The current is flowing I, so magnetic field B1 would be how much? That would be mu naught I by 4 pi and sine 45 plus sine 45. So how much is sine 45? Sine 45 is how much? What is the value of
3 by
sine 45? Put 3 by 2.
1 by
That
root
is
2.
1 by 2.
1
Yeah, 1 by 2.
by 2.
Yes, yes, 1 by 2. So then this is mu naught I by 4 pi. And this is 2 by root, right? So then we can put this value in here. So 4 and mu naught I by 4 pi into 2 and a square and mi. So I and I will cancel and mutual inductance you will get 8 and mu naught by 4 pi a square. So that would be the answer, right? So what is the options that we have? What are the options that we have? Yeah, so mu naught by 4 pi and it, yeah, there is. Also, we had this b by 2 as well, right? So we didn't write this b by 2 in here. Right? So this b by 2 is also there. So this 2 will come up and this is b, right? So this would be 4, right? And we can cancel this root 2 in here. So this would be how much? So this part would be 8 by, so this would be the, this magnetic field B1 is how much? Mu naught I by 4 pi. So if we put this value in here, right? So if we put this value in here, so this is mu naught I and 2 divided by 4 pi. So 4 into 2, 8 root 2 and by b. So 8 root 2 by b mu naught by 4. Mu naught by 4 pi 8 and a square by. So that would be the answer. Right. So what did we use? We use this inductance rule. That inductance would be how much? Inductance. So flux would be directly proportional to current. So from there we can calculate this inductance, and then we know that flux is how much BA. Area which is there in this flux is this small area, right? And then there are four contribution of magnetic fields. One is this, the other one is this, and all these are same. So we write it as 4B1, and then we calculate this B1, and then we put this value. So this way we can get this mutual inductance. Please note it down, and if you have any question, please tell me. So please tell me if you have any question. Otherwise, please take it down. And whenever you want me to, yeah, whenever you want me to scroll this screen in the right direction, then please tell me. First, note down the question and then down the answer. Okay, yes, Abdul Rahman, you are here for which class? You have joined, but you are not replying. Let me ask the learning meeting, right? And Tarif, whenever you want me to scroll this screen to right hand side, please tell me. This would be the correct. From here to here, yeah. So that this part is p by 2. And then we apply the magnetic field of a finite wire. Yeah, whenever, Tariq, you want me to scroll this screen in the right hand side, please tell me. Yeah, so okay, I have talked to the Learnivio team and you are in the wrong link up to Trenman, right? So, okay, so you have got the correct link, right? Did you get the correct link up to Rahman? Yeah, please join in that link because you are in the wrong class, right?
Uh, Sir, can you say it again?
Yeah, yeah. Did you get the other link in the chat box? Can you please check your chat box? So in the chat box, you must have got a link because you are in the wrong class, right? Please check your chat box, and in there you have got this link. So please join in that. Okay, 4 classes happening in that.
I should join a different class.
Yeah, yeah, yeah. So did you in the chat box? Did you get any link of the class?
Yes, I got it.
Yeah, yeah, yeah. Please join in that because you have to join in that class. Yeah. Sorry for this confusion, Rafishan. Yeah, so you have to join in that.
It's okay.
Yes, sorry. Noted what part you are taking down. And please revise the previous chapters, right? Otherwise, you will forget everything, right? Yeah. Yeah. So in there, we have used the finite one because the separation was p by 2, and then we calculated the magnetic field, then we put this magnetic field in here. Whenever you have noted it down, yeah, whenever you have noted it down, Tariq, please tell me. Yes, Tariq, noted. Are you there, Tariq?
Yes, I'm writing it.
Yeah, yeah. I thought you went for your Sala, but yeah, don't
No, sir.
go. After this class, you please go and yeah, your Sala. But yes.
So the Salah is already ended. I prayed before the class started.
Oh, good, good. Yeah, good. And please pray for me also, right? Remember me in your duas, and I will also. Let's say if my dua is not working, then your dua is working. Then yeah, so then it would be good for me. And let's say my dua is working and your dua is not working. So in this way, we can increase our chances, right? Yeah, whenever we have noted that
Yes, sir.
done. Okay, so yeah, then let us do the next question and this chapter. Next question is about the energy, right? And what is the energy that we already know? So energy is how much is the energy that is half Li square, right? This thing we already know. So the question is, yeah, this is the question. Okay, a coil of inductance 2 Henry having negligible resistance is connected to a supply of source of supply whose voltage is given by this thing, right? So you have an inductor, right? You have an inductor which has a negligible resistance, and this is connected. You have an inductor, and this is connected to some voltage supply, right? And this is not sinusoidal, but this is varying like 3T, uh, right? So voltage is varying like this, and this has Henry inductance. Now we have to find out if the voltage is applied when t equals to 0, then the energy is stored in the coil after 4 seconds, right? So we have to find out the energy stored after 4 seconds. So to do that, we know that how much is the energy, right? So we know that this is half Li square. So we have to find out this I, right? This is the thing that we have to find out. And what is given? The EMF is given. So EMF is equal to how much? What is the EMF? You remember? EMF for the inductor is how much? What is the EMF for the inductor? Do you remember? This is L di by dt, right? Right, sorry.
So
This is the EMF, right? So if we put this value, what is the EMF? This is 3t, and this is equal to L di by dt. So if we write this thing the other side, if we take this thing in the other side, so this is 3t dt, right? And then we write this di. Okay, we take it. We can write. If we take this L the other side, this is 3 by L at d dt. So how can we get the current? To get the current, we have to do what? We have to integrate both the sides, right? So integrating both the sides, what we will get? We will get di and integration of 3 by 2 d dt. So integration of di would be how much? What would be the integration of this thing? Yes, what would be the integration of this thing? Yeah, what would be the integration? Di. That would be simply I, right? And this is 3 by L is constant and we have d dt. So then if I calculate, if I integrate this thing, what would be the integration of this thing? What is the integration of t with respect to dt? What is this integration? This is similar like this one. So what is this integration? Sorry,
x square by 2.
x square by 2, right? So why you are confused with this t, right? This is same as, so this
It's a
would
t
be
square by 2
t square by 2.
plus
This
c.
is t square by 2. And yeah, let's say that we don't, right? So this is indifferent integral that we write because we don't know this, yeah, we don't know this limit. So let's forget about this c part, right? Because v is varying like 3t. So at t equals to 0, v is 0. So current would also be 0. So we can take this 3 as 0, right? So yeah, you are correct that this would be plus c, but this is vt, 3t, right? So if v is 0, then current would be 0. So we can take our c to be 0. So this is our current. Now they want us to calculate the energy at 4 seconds. So what is the current at 4 seconds? That is 3 and 4 square by L into 2. So this is how much? 3 into 60 divided by 2L. So this is 8 ja. So 24 by. So current now we know, right? That is 24 by L. And we know that what is the energy? That is half Li square. This would be half L. I is 24 by L and 24 by L. So 1L will cancel. And this would be how much? So this would be 12, right? And this is 12 into 24. And L was how much? L was 2 Henry, right? This is 2. And this is 12 again. So 12 square is how much? 140. This would be the energy. Is it clear?
Yes.
Okay, then please. Let me take down. And whenever you want me to scroll down, please tell. Then this chapter would be over because we have done inductance, we have done mutual inductance, self-inductance, we have done EMF, we have done energy of the inductors. There's this. Yeah, whenever you want me to scroll down the screen, please. Yeah, whenever you want me to scroll down, please.
So can you scroll down? Is certain.
Okay, so the new chapter that we are going to start is AC, right? So we already know that, and I would like the result, right? That we have understood that by rotation we can also generate the EM, right? So if you remember when we were doing this part, right, when we were calculating the EMF, so EMF we can change by changing B, by changing A, by changing theta. So this theta part gave us the EMF, which was what? This was B A omega sine omega t. Do you remember this thing? Do you remember this thing? Yes. So we had this magnetic field and we had this coil aperture, right? And this area was fixed, only this thing was rotating, right? So only this thing was rotated, and then we generated the EMF, which was like this, right? And then we write it simply as E naught sine omega t. So this kind of EMF we will be talking about in this chapter, right? So what is the variation of this EMF? So the variation is from 0, let's say this is angle pi by 2, then pi, then 3 pi by 2, then 2 pi. And then this is periodic, so again it will repeat same. So at, let's say this is, so this is E naught line, this is minus E naught line. So at 0, this is 0. And at 90 degree, sin 90 degree is what? 90 degree is what? Sin 90 is what, Tani? Yeah, sin 90 is what? Sin 90 is 1, right? So at 90, this sin 90 is 1, so this E becomes E naught. At 0, sin 0 is 0, so this is 0. So E is 0, and then at 90, this becomes E naught, and similarly, at 180, it becomes 0. At 3 pi by 2, it becomes minus E naught, and at 2 pi, it becomes 0 again. So this is the variation of the EMF that you have for this kind of behavior. So this is sinusoidal, right? This function is sinusoidal, and this will repeat again. So this will be same in the next cycle also. This is the behavior, and then we calculate three things from here, right? Then we calculate, right? So this E is E naught sine omega t. So this E naught is peak voltage, right? So we can see that the maximum voltage is how much? That is E naught. So this E naught is peak voltage, and then we have three parameters. This E is we calculate three things from here. So one is the average EMF in full cycle. Then we calculate average EMF in half cycle. Then we calculate ERMS. Right. So I will directly write the result because this part we have already done. So this is 0. This is E naught by pi. And this is how much? This is E naught by 2. Right. These things we have already done in your CBSE class. Right, Tari? Right. Is this clear? Yes. Is it clear, Tari? Yeah, Tari. These things we have already done in your CBSE part, right?
Yes.
I will not read this part. I will directly write the results. And we also know that how do we define the average. So average of a function, define it like this 0 t f t dt divided by this that. Right, so that is how to define the average of a function. Right, and if you have, let's say, if you have two currents, right, which are let's say if you have E, which is E naught sine omega t, right, and then we have let's say E2 sine omega t, right. So then for this case, E RMS square, that would be how much? That would be E naught square RMS, right? This result is important. So that would be E naught RMS square plus E1 RMS square. So you have to remember this result very carefully. So I mean to say that, yeah, I should write it properly, right? Let me write it in this way. That let's say your EMF is the sum of two wave function E1 plus E2, right? Then you write your RMS. So then your RMS of this thing square, that would be E RMS of 1 square, and then E RMS of this is the important result that we right. So you please note down these things, and in the next class we'll do some questions from it. So please note it down. Yeah, please note it down. In the next class, what disconnected. Yeah, please note down this part, and in the next class we'll do some questions to understand this thing clearly.
Yes.
Yeah, whenever you want me to scroll down, please tell me.